Hello. Today the plan is to start this very bottom-up way of talking about perception with vision by starting with the property of light, or the properties of light, so the electromagnetic energy out in the environment, the stimulus. Introduce the eye, so the mechanisms of the eye that get that information back to the photoreceptors, so those sensory neurons that are going to help us do the very first bit of processing so that we can communicate this information to the brain. And there are two ways to conceptualize light or the electromagnetic spectrum. That is one as a wave as it is moving through the world, and we will have to talk about it that way since we'll talk about different wavelengths and what that means for our perception of color. And then two, as a stream of photons. So it is made up of these photons, and we need to talk about it that way as well, because when it is absorbed by those little retinal molecules in the sensory receptors, they are absorbing photons of light. So it is always fun to look at the electromagnetic spectrum as we start with those really, really tiny waves. So like picometers down at gamma rays, moving into nanometers, into X-rays, so nanometers being a billionth of a meter, and then ultraviolet rays, and then you can see the next part of the electromagnetic spectrum is visible light, so what we actually see of the electromagnetic spectrum. And you can also see as they go from shorter to longer, we're going, I'm going to go the other direction because Roy-G Biv is easier for me to say in that order. As we go from longer to shorter, we go from red in the longer wavelengths to orange to yellow to green, to in the shorter wavelengths, blue, and then indigo and violet in the shortest wavelengths that we see. And then as we get into shorter wavelengths, we get into ultraviolet light. And some animals do see that ultraviolet light. So hummingbirds, certain insects like bees, some fish. And then as we get into longer and longer wavelengths past the 700 nanometers that gives us the red part of the spectrum, we get into infrared rays, where some animals see in the infrared part of the range. When I say see, I might want to put that in quotes, since a lot of the times they're kind of sensing that heat with their pits or with their tongues. And then we go farther on out into getting radar, the different kinds of radio wavelengths, TV, and so forth. When you look up, so if we look at that little part of the spectrum that we see, the piece that's at the top there, it shows what aspects of those waveforms are, how those are translated into perception. And so if we look at the wavelength from peak to peak, that wavelength is what I'm talking about here. From 400 to 700 nanometers is the wavelength from peak to peak, where we get from the indigo violet part of the spectrum up to the longer wavelengths of red. But if we look at colors, so if you kind of look at the blue, if you can, of my shirt, it's not going to be a rainbow blue. It's not going to have that perfect sine wave or sinusoidal waveform. It's going to instead be a mixture. And so at the bottom it says purity, which really is a mixture, is typically what we see. And the mixture gives us the saturation, where it can be, we can make it lighter and lighter with white, like with pink, and we can desaturate that red and make it more pink. We also have amplitude, so the height of the waveform is based on how much or how bright that color is, and that depends on the illuminant, right? So I'm under a relatively low level light, and this is going to be a shorter wavelength than if I go out into the sunlight, and then it's going to get up higher and get a higher amplitude, which is going to make this appear, this blue, which you can barely see at the bottom there, a little bit brighter. And again, this is not going to be the perfect sinusoidal waveform or sine wave. It's going to be a purity, I mean, it's going to be a mix of various wavelengths in that shorter waveform, really. And so this light information is going to, it comes from some illuminant, let's say the sun. It is getting reflected. Certain wavelengths are being absorbed and other wavelengths are being reflected. In this picture, the tree is reflecting certain wavelengths, right? So some in the middle of the spectrum that are going to give us this green color, and then some that are kind of across the spectrum and really messy. It's really an extra spectral color is brown. And so that information gets taken in through a lot of optics of the eye. The very outer part of the eye is the cornea, and it's doing a lot of the bending or refracting. So bending and refracting is the same thing of light. It's doing about 65 to 75% of the focusing power of putting that information back on the back of your retina, where we're going to have those rods and cones. Okay. It's also then going through the pupil, which is being controlled by the iris. The pupil is the hole that lets the light through, and the iris is controlling the size of the pupil. And for sensation and perception, I usually just say it constricts or dilates the pupil depending on light levels. So if I'm out in the bright light, I'm going to constrict the pupil, and if I'm in the dark, I'm going to dilate or make the pupil larger so that I can let in more of that very low light level. And we, in sensation and perception, ignore the autonomic nervous system and being nervous. That's for other classes. And then behind that, so we have the cornea, it goes through the pupil, and it also goes through this lens, which is actually what's going to do, it's going to do less of the bending of light, but it's going to be able to change so that we can allow for accommodation, and I can focus on the back of the retina what I'm looking at, depending on whether it's close or far away. So it's helping to focus the image on the retina, and the ciliary muscles are controlling the shape of the lens. Here are a couple of terms you can let wash over you. You don't have to know these, but I feel weird leaving them out. So the aqueous humor is between the cornea and the lens, and it's really doing the nourishing and removing waste from those regions, okay? Bringing oxygen to those regions. And behind that, the vitreous humor. So if you poke your eye, don't poke your eye. If you poke your eye really lightly, you can feel this kind of gushiness, which is not a technical term. That's the vitreous humor, this gel-like substance. I always thought it was really interesting when I learned this, that is creating those floaters that when you're looking around and you see this little floater, you're kind of following that around with your eye. That is pieces of vitreous humor coming off. And we all have that. It does not regenerate itself, but the vitreous humor, we all see those floaters, probably about the same amount. And then some of us pay more attention to them than others. And I did move my picture so that you can a little bit see now that we are taking that information that's being refracted by the cornea and the lens, and we're getting that information so that it's in an inverted kind of flipped image, right? So instead of seeing my hand in this way, you're going to see it on the back of your retina inverted and flipped. And we're going to see that this continues so that we're in the visual cortex with this inverted flipped image. Well, what we want, and the point of all of these optics of the eye, is to focus the light on the foveal retina, where the retina is where the action's taking place. Basically, this is where those rods and cones, the photoreceptors, the sensory neurons that are going to change that information into action potentials for the brain, that's where they live, is back there on the back. And you can kind of see in this picture this magnified part over to your right, where you can see the rods and cones, the very outer discs, back against that pigment epithelium. I'm going to keep coming back to that. And you can also see maybe that it's pointing to this foveal area where you can't really see it in this picture, but there's a little dip in the neurons, so there aren't neurons there. The cones, those particular photoreceptors, get a really as direct kind of information about light as possible, and they're tightly packed in there so that when we want detailed, acute kinds of information, like looking at letters on a screen, we're going to point our eyes so that that information lands on the fovea. We also have a blind spot, so you can see with the retina of the eye in the back that we have to get that information out, right? You can see this little optic disc, or the axons coming from the optic nerve leaving the eye. We also have blood vessels coming into the eye, and in that little area that's leaving the eye, there are no photoreceptors there. So that's a blind spot. as I said, the goal of all of these mechanics is really to focus light on the foveal retina. It's good to become consciously aware of this accommodation thing, which you've experienced many, many times in your life, but I'm going to tell you a way to sort of become aware of it. If you take a pen or pencil and you kind of move yourself back a little bit and you focus on this screen, your lens is going to be kind of flattened out so that you can see what's far away. Okay, and when you're doing that, what you'll notice is what's on the screen is in focus, and that pen or pencil or whatever, it's blurry, and you probably have some double vision of it. And now if you change your focus so that you're looking at the pen or pencil, you'll notice that the screen becomes blurry, right? And probably has some double vision to it. My pen's too close. Okay, but what's happening now is the light's coming in at an angle. And so now we're going to fatten up that lens so that it bends the light more to get it focused on the retina. That's just becoming aware of this accommodation of the lens is changing its shape to accommodate for whether we're looking at something close versus far away. This is the screen I usually put up and see if there are questions. So you might pause it and see if you have questions and ask me. Okay, so some clinical issues at this level of processing, at the level of really the mechanics of the eye, and in this case, the lens and the cornea. The first one is myopia, or what's known as nearsightedness. That really what's happening is that image, instead of getting all the way back to the retina, it's being bent too much, and so it's getting focused somewhere in the middle of the eye, and so by the time it gets back to the retina, it's blurry. And there are two ways that this can really happen. One is a refractive myopia, so the lens and cornea are bending the light. They themselves are doing too much bending of light. But there's also an axial myopia, which is the eyeball being too long. And so someone's lens and cornea are basically bending light like a quote normal person, but their eyeball is longer, and so it's still not getting all the way back to the retina. I will say this is the kind of myopia that I have, apparently, as I've had a doctor talk to me about my eyeball being too long before, and I was like, oh, so I have the axial myopia, apparently. So myopia, we have more than 70 million Americans have myopia, and it is to some extent genetic and to some extent environmental, and it does look like we have more myopia in developed nations because we are doing things like looking at our screens a lot, getting too close to our screens, looking at books, and not looking out far away, and really just exercising those muscles as one suggestion. In hyperopia or farsightedness, it's really that the lens and cornea are not doing enough bending, and so when they go to bend the light, it's not getting focused on the retina. It's getting it would be focused somewhere behind the retina, but instead what we see at the retina then is going to be a blurred image. And your author has written down that we don't really have an issue with hyperopia, but then he mentioned something about glasses. So both of these are very correctable with glasses, and myopia is also correctable with a laser surgery, where typically what they're doing is shaving off some of that cornea because it's doing too much bending, and so we just take some of it away. What is like hyperopia and definitely exists in people is presbyopia, which means old sight, and I resent the term, as I have some old sight now. I have those progressive lenses where they're for my myopia everywhere, except they kind of progress down so that if I'm looking at a screen or reading something, I have to point my eyes down at that, and then they're kind of magnifying things a little bit for me. And so what you'll see, what happens as we age, is The lens becomes a little bit more, it has some thicker, like crystalline to it, and the ciliary muscles get weaker. And so those two things together mean that I am not bending light as much anymore, and so it's more likely to get focused behind the retina. And we'll typically see what it's showing at the bottom is as we age, that near point where I can see and I can bend light enough, it gets farther and farther away. Okay, so we get that information back to the retina, to the rods and cones. So the photoreceptors, they are our sensory receptors that are doing the transduction. Transduction! Remember to sing it. It's a very exciting thing. We're going to go through the differences in those rods and cones, and then what that means as far as our particular, how we see as humans. So the differences, they differ in their physical appearance. They differ in their distribution across the retina. They differ in their wiring, which we're going to walk through that and discuss how the wiring means that the cones are going to give us more acuity and the rods are going to give us more sensitivity, and by that I mean sensitivity to dim light, to low light levels. We'll talk about some clinical issues at the level of the retina now, and then that will start to show you the functional significance of the rods and the cones, but we'll go through the functional significance as well. So they look different. Their appearance is different. The rods look like rods. The cones are smaller, and if you use your imagination, they look like cones. This is a scanning micro pictograph of rods and cones. Their distribution across the eye is different. So if we're looking at 0 degrees, and the way they do this visual angle is if I'm looking at 0 degrees, that is where I am foveating. That's where my eyes are pointed, regardless of which way they're pointed. The 0 degrees is my foveal vision. And around that, because the retina is round, we're going to have these degrees like the degrees of a circle. Okay, and so if you look at the 0 degree mark, the red line is the cones, and you'll see we have lots and lots of cones packed into that foveal vision, and then they trail off really quickly, and we have some cones out in the periphery, about the same amount of cones as other areas of the periphery, and they're just not very many cones. If we look at the rods, the blue lines, you can see that there are no rods, none in the foveal vision. Okay, we're going to end up coming back to that. As we move out into the periphery, as we get close to the fovea, we'll see a large number of rods. We want pretty good vision right where we're kind of pointing our eye, close to where we're pointing our eyes, even if we're in the dark, but then those two are going to trail off. As we get farther and farther into the periphery, if you kind of bring your consciousness to your periphery, like I have my hands out here, it's kind of blurry, right? The other thing this picture shows is that blind spot. So that brown area is where the optic nerve is going in, and you can see it better on that picture on your left as well than you could before. The optic nerve, the optic nerve is leaving. It's not going in. The optic nerve is leaving. We're going to take the axons from the ganglion cells that are going to bring that information to the brain. They have to leave the eye, and then we also have blood vessels going into the eye. And so there are no rods and cones there. And I typically hand out a really quick and dirty, cheap example of us actually seeing our blind spot. But if you want to see your blind spot or become aware of your blind spot, you can print this page up whole, close your left eye, and then line up the cross so that you're looking at it with your right eye, and move the paper towards you until the mouse disappears. And what do you think happens to the stripes? And after we've done this in class, people are they're pretty good at guessing usually. I do this with a blank piece of paper and just an XYZ, and your brain fills in with the piece of paper. Your brain is going to fill in those stripes. You could also, if you want, if that one didn't work very well for you, because I have noticed that some people tend to move one of their eyes a bit more. You really need to keep your eye fixated on the fixation point. You can print up this page, I think as a whole, but I think half page might even be better. I haven't actually used this one. I've used it from the book, but then you close your right eye and you look at that fixation, move it back and forth. And what do you think happens in the middle? I'll let you think about that.